Hi everybody, this is Sushanta again, and so we have seen some past lectures where I talked about the LNA design, and we have also extended that to talk about the mixer. So we have done that, and I thought this would be a good point to actually talk about the RF systems. And by RF systems, what we mean is we treat the whole receiver more like a black box, and then try to derive some specs for that black box. And once we have got the specs for the whole system, then we try to go down into each block and try to derive the specs for what should be the specs for the LNA, what should be the specifications for the mixer, for the filter, and everything else. So let's say if you were starting over, right, and you want to build an receiver for say GSM or maybe WCDMA or LTE, they have got different levels of different modulation schemes, different requirements, different jammer scenarios and all that, and you might first have to do what we call as an RF systems analysis to treat the whole receiver as a black box and then come up with a set of specs for this black box. And when you have done it at the system level, at this black box level, then you will go down and try to derive the specs for the blocks itself. So this is a very, very important process, because as a designer, sometimes you go to the industry and you're given a block, you're given the specifications for the block, and you're just fighting to meet the specification only. You don't have the visibility outside of your block. Let's say you're an LNA designer. It's not good for you just to have visibility into the LNA itself and not into the other blocks. It's good to understand, even at a top level, how is the system architected, because when a designer understands that, then there are many knobs the designer has in his pocket to tune around and make the system more efficient. And that's why I think that I learned it, and I think that it will be beneficial for everybody to get knowledge of these RF systems. So if we treat the receiver as a black box, which is shown here, it's consisting of the LNA, the mixer, the low pass filter, some PGA, programmable gain amplifiers, for going into the ADC. If we treat the whole thing as a black box, then that output goes and talks to the modem. But what are the different specs we can come up with here? Some of the things that I could think of, and this is not a completeness list in any way, but I'm just putting down what I can think of, is gain. What should be the gain of this receiver? Let's say from the RF input here all the way to the ADC input, what should be the gain of this thing? Now the RF input, it could be small. When it's small, we will like to have some high gain. But when the input gets big, then you don't want a high gain. You will saturate this receiver. So what should be the gain, and how should it change over different input power levels? So there is a dynamic range here of the input. For example, you could have most of the systems starting at a lower level of say minus 110 dBm. It could go all the way from minus 110 dBm to 0 dBm. Okay, so that's 110 dB type dynamic range you have of the signal. If you're very far away from the tower, you could be minus 110 dBm. In some extreme cases, you could be very close, where you could be almost like 0 dBm. So how do we design it, and what should be the gain? How should it change over different as the input changes? We have some exercises later on where we'll go into more detail of how we do AGC and when do we switch the gain and all that. So AGC stands for automatic gain control. We'll look into that, but sorry, I'm getting distracted. So let's come back to this list. So as a black box, gain is an important specification. Noise figure, what should be the noise figure of this whole chain, because that is directly related to sensitivity. What is the minimum signal you can detect at the input? So we'll look at noise figure, then we'll look at different linearity requirements given in terms of what should be the IP3 of this whole black box, again as a function of the input. The input will be changing, so how would it be? So again, that exercise, as I talked about, we have two exercises in this lecture at the end, which will actually capture how do you architect the system, how do you come up with IP3 numbers versus the whole dynamic range of the input. Similarly, IP2, which is the second order distortion. Then there is another thing that I haven't talked about while we were doing LNA and the mixers, which is called as the RSB, and it's called residual sideband. And it has got two components. One of them is the gain error, another is the phase error. And this is between the I and Q channels. Remember, I'm only showing one channel here, but actually there are two identical channels, one I, one Q. And what we are saying is, since they're identical, they should not have any error in gain. But there is always going to be some finite error in gain between I and Q. That is the gain error. And the phase, when the mixer clock comes in, right, one mixer versus the other mixer, they are 90-degree phase shifted, I and Q clocks. That phase is not going to be 90-degree exactly. There is always going to be some phase error. So because of the gain error and phase error, it gives rise to something called as RSB. It is what we use in the cellular world, but it also has other names it uses. And so this is like a zero IF system, where you're down converting right to the baseband DC. But if you had a low IF, a similar thing also is known as image rejection, where you have two paths that you're trying to combine to make a complex filter to reject an image. And in those kind of systems, you're going to always have some gain error and phase error, which will give rise to a similar phenomenon where the image that we're trying to cancel in super heterodyne receivers, that image will have finite image rejection. So I just wanted to mention it, but I don't want to distract you away from this. We are talking about zero IF systems, and we are talking about the gain and phase error between the I and Q channels. So we'll look at each of these in more detail. But overall, these are some of the specs that you would like to understand for this whole system. You'd like to derive these for the whole system. How do we derive it? It's shown in more detail after we go through each of these, and I tell you a little more details about each of this, and then you will see those exercises will capture it. Okay, so let's start with the first one. I'm not doing the gain first, but first we're going to start with the noise figure. Okay, so the noise figure of this receiver is directly related to the sensitivity. And let's see, how do we normally define? So this you might be already familiar with it, but if not, let me explain this. So the sensitivity of a receiver is kind of given by this equation. It's -174, and we are talking about sensitivity in dBm numbers. Okay, so there is a term -174 plus 10 times log of bandwidth. This is the bandwidth of the signal that finally gets down converted, goes through the filter, goes through the ADC, and the ADC is seeing this bandwidth. Because what this ADC is going to do, it's going to do the analog to digital conversion only of the signal and all the garbage in a certain bandwidth. And what is that bandwidth? That is the signal bandwidth. That is what is this bandwidth here stands for that. Okay, this is not any RF bandwidth. After down conversion, it is actually the baseband bandwidth. In baseband, what is the bandwidth we are talking about is this. Okay, and then we have other terms, but let me explain where do these two terms come from. So let's say we didn't have all this and we have free air. Even in free air, we know that there is a finite amount of noise that is already there. And if you wanted to know the noise, as given by this equation KTB, where K is the Boltzmann's constant, T is the temperature in Kelvin, and B is the bandwidth of interest that we're talking about. So if we took any bandwidth, and we say some 1 megahertz type bandwidth, okay, there is always going to be thermal noise. That is the limit. You cannot, you just can't have any noise lower than this. This is as given by the physics, as it's given here. KTB is this. So if you put the value of the Boltzmann's constant K, and then temperature, and let's say the temperature, room temperature is 298 Kelvin. It's 25 degrees centigrade, 298 Kelvin. If you do this two product and to get 10 times log of that, it will give you this -174 number. So this -174 number is nothing but just simply K and T. Okay, this bandwidth is shown here 10 times log of bandwidth because we are deriving sensitivity in dBm. So this is the physical noise limit. You cannot have noise any less than that. So you are always there. If this is the noise, which is the physical limit, then on top of that, when we put this guy here, right, this black box, and we say it has some noise figure, we have to add that noise figure, because that noise figure is in dB is a measure of how much more noise is this guy adding. If you look back at the definition of noise figure, it gives you signal to noise ratio at the input and signal to noise ratio at the output. It's a ratio of two things. So in a way, what it does is it just gives you an amount of how much of noise has this guy added. And so we have the physical limit, which is this term. Then we have the noise figure that is caused by the chain. And then the modem needs some signal to noise ratio. You cannot just say, okay, my signal is going to be same as the modem and this is what the sensitivity is. There are different standards, like GSM, it has a different modulation scheme. Okay, so when you're receiving the signal, it is modulated, and this guy wants to demodulate it. So he will need a certain signal to noise ratio. As the modulation changes, say CDMA, WCDMA, LT and all, they all require different Wi-Fi and all, they all require different signal to noise ratios. So whatever the signal to noise ratio is needed by the modem here, we also have to add it. So here is the noise, physical noise. On top of that, you add the noise added by the receiver black box, and then on top of that you add the SNR that is required by this modem. That gives you what is the minimum detectable signal here, which is the sensitivity. That is how we calculate the sensitivity for a particular standard, and it depends on, as I said, the bandwidth. Then the higher the bandwidth, the sensitivity number is going to be, you can't detect a very low signal. As you can see, this number is going to be higher. If the SNR is higher, then also you cannot detect a very low signal. Your signal goes up as the minimum detectable signal that you can detect. Let's take a table here to kind of explain some of the different cases that we have, and I just wanted to go over them to show you how we use this formula and calculate it. So the case here is, I have kind of tried to note down some cases at GSM, WCDMA, LT 20 megahertz mode, and Wi-Fi 4 cases. For each of them, I'm saying, let's assume that the black box noise figure is 2 dB. Okay, for GSM the bandwidth is about 200 kilohertz. WCDMA 3.84 megahertz, LT 20 megahertz, I'm using 20 megahertz bandwidth, and Wi-Fi is also around 20. For the 20 megahertz case, I'm using this. Okay, so we have plugged in some numbers for this, plugged in numbers for this. Now the one remaining is we have to have the SNR. Now the SNR for the modem, again, as I said, is these different standards have different modulation schemes, and in order to demodulate it, the modem will need certain SNR. For GSM case, it needs 9 dB SNR. So if you look at this and we plug all these numbers back here in this formula, you will get a value of about minus of 110 dBm, which if you convert it to voltage is about 1 microvolt. Of, like, if you had a sine wave and you wanted to know the peak amplitude, it will be about 1 microvolt. That's how low of a signal these phones can actually detect. It's amazing, it's so small. So this will be the sensitivity number for GSM. Now if you go to WCDMA, again we have all those values. Now the SNR, see the WCDMA, what happens is for WCDMA, LT and Wi-Fi, the information is not received in a single carrier, it's like a multi-carrier modulation, like OFDM, orthogonal frequency division multiplexing. So the information is not carried in a single carrier, but it has got a lot of sub-carriers, a lot of multiple carriers which carry it together, and I think I have some pictures later on to explain this more. But there what happens, many of these systems can actually work for 0 dB SNR or even negative SNR. Why? Because imagine you had 1000 subcarriers. Your information was coded into 1000 subcarriers tightly packed together. If you lost a few of those subcarriers information because of noise, you still have information in the rest of the subcarriers, and that's why these systems are more prone to noise or things like that. So that's why they can actually work with negative SNR also in some cases. WCDMA could work even up to an SNR of, I've seen literature which says minus 18 dB. You could design your modem where the noise could be 18 dB higher than the signal overall in the whole band, not just a single subcarrier, not for all the subcarriers, but only for a few carriers. It's more, few less, but overall like 18 dB so it could run. I've just put a number here, -4, just for the sake of calculation here. What I'm trying to show is GSM and WCDMA to get the same sensitivity number. Even though GSM needs 9 dB SNR, in WCDMA you can do it even with -4 dB SNR, okay, at the modem. But again, this thing varies. There are different numbers for it, and based on how you're implementing a modem, the modem team normally would come back and give you that this is the SNR I need from you guys. To the RF team, they will convey this information. And even as an RF designer, you should know this so that you can help architect the system. LT 20 megahertz, again, I made an assumption here of 0 dB. Okay, just to show a calculation. But again, you have to get this number. But if this was the number, what will be the sensitivity that's showed here? Wi-Fi For 20 megahertz case, I think the SNR is 14 dB, because when you're transmitting at high data rates, you need to maintain very high SNR, otherwise you will lose data and your data rate will go down. So with the high SNR value, the Wi-Fi's have a sensitivity of about minus 85 dBm with a 2 dB noise figure. Okay, so if your noise figure is higher, the sensitivity number will actually degrade more. So that is how the noise figure plays into the picture, and that is the significance of noise figure, and from there how do we determine sensitivity. Okay, so I hope that is clear here. Next we go to the gain. So one thing I mentioned is that this input here, the input is actually not a single value. You're not going to receive the signal at minus 110 dBm all the time, no. It has a huge dynamic range. It could go, as I mentioned, from minus 110 dBm low end all the way up to 0 dBm. So the gain in this thing has to change. It has to be adaptive, which is what we call automatic gain control. And we'll talk about that later. But right now, let's first see how do we calculate the max RX gain, the maximum gain. So when the signal is the smallest, you have the highest gain here, right? And why do we want highest gain? The reason we want highest gain is if I define my gain from the LNA input to this ADC input, then I want all this noise of the ADC to be suppressed. Remember, each block is causing noise. If you have more gain in front of it, you're basically suppressing its noise. So if you have more gain, you can suppress more of ADC noise. That means the ADC design becomes easier. You don't need to have a high dynamic range ADC there to do that. So that's what I'm going to explain here. So let's see how do we calculate this max gain. So we have the ADC normally, there are many specifications there, but the specs we are more interested in, what's the full swing and what is the dynamic range. The full swing is normally given as X volts peak to peak number, and the dynamic range is a measure of what is the max to min, the min in this case being the noise. So there are different definitions of dynamic range which could mean different things, but here in this one what I'm referring to be very clear, is this dynamic range number will tell you what is the maximum swing allowed, some X volts peak to peak, and the lowest is where is the noise. I'm not talking about any distortion or other things at this point, but just to get the noise. Okay, so let's take an example where the full swing, let's say, is 1 volts peak to peak. Okay, which means again it's a differential swing, so it goes 500 millivolts up and 500 millivolts down. Okay, that is what is at the input of this ADC. Now you can convert this voltage number into a dBm number, because whenever you go from voltage to power, you have to define what the impedance is. Since we start with a single-ended 50 ohm system, we can assume that this differential is 100 ohms, even though there is not a real 100 ohms present there. But all I'm doing is I'm taking the voltage level and I just want to convert it to a dBm number across a 100 ohm, a superficial 100 ohm. So if you do that, what happens is the power, the RMS power is V RMS square by R, right? But you can represent the RMS as if you have the peak value, V peak by root 2, square root of 2 will give you the RMS value. So I really want an RMS voltage square by R, which I can represent as V peak square by 2 R. Where does this 2 come from? This comes from the fact that the RMS voltage is V peak divided by square root of 2. Okay, so here if I plug in these values for this specific case, I can plug in this as 0.5 volts, R is 100 ohms, RMS value of PRMS will become plus 1 dBm. Okay, so this would be the maximum swing and the corresponding power, RMS power across 100 ohms if there was a 100 ohm impedance there. Now what happens is that we're trying to define the signal to noise dynamic range. Okay, this is again here what I'm defining the dynamic range is, if I know, if I'm given that this dynamic range is 60 dB and my highest power level is plus 1 dBm as we calculated here, then the noise level is minus 59 dBm. It's the maximum minus the dynamic range value. Do not get hung up on the fact that this could have different meanings at different places. No, I'm not really trying to refer to anything like that. All I am saying is that I just want to know where is the noise floor. That's all I'm trying to calculate. So by doing all this, we have come to a point where we say, okay, the noise floor is 59 dBm, minus 59 dBm, which is the ADC's noise floor. For this case, where the ADC is a 60 dB dynamic range ADC. So now we say that we have, so we draw this black box, and we say that the sensitivity, let's say for GSM or any case for that matter, we are saying, let's say the sensitivity I want 110 dBm. Okay, and I want this to be for a case where the noise figure is 2 dB here, for this whole chain. So, and you also say, okay, I want a sensitivity minus 110 dBm, which is what kind of as an example we did previously, but I want the ADC noise to be below that. Okay, how much below? So 10 dB further below. So I want the ADC noise to be minus 120 dBm. So my sensitivity is minus 110 dBm, and my ADC noise is minus 120 dBm here reflected at the input. So if it is minus 59 dBm and this is minus 120 dBm, what is the gain you need? You need a gain of about 61 dB. So knowing what the ADC is, knowing what its power level is, I mean the noise level, we want it to be divided by the gain so that it remains at a certain level that we are desiring it to remain. That's how we calculate the gain here. Okay, now you can see that more and more gain is good because it will suppress the ADC noise more and more, but what it will also do is what we will capture in the exercise later on is, remember we have a signal but we are also going to have interferers here. Having too much gain in this channel, what it would cause is it would actually cause the receiver to saturate because of those jammers. Because those jammers are strong. They are not minus 120 dBm or minus 110 dBm. They are much stronger than that. So there is a trade-off. Having more gain in this chain helps suppress ADC noise, but having too much gain also could cause saturation of the receiver and also exceed the swing at the input. So whether it's the signal swing or is the jammer swing, we don't want it to exceed a certain maximum swing limit that we have. Like in this case, we said it's 1 volt peak to peak differential. So there is a trade-off, and you have to iterate it to see what do you want to do, right? How much gain can you tolerate, so that there is a balance between both these opposing factors here. So now let's continue this case and try to do a little more here. So what did we say? We said, okay, we want a sensitivity minus 110 dBm. We have 2 dB noise figure here. And we said that, okay, let's just for the, because see, this is also going to be an iterative step, which is what I'm going to describe next. But the first step of the iterative step was more like saying, if the sensitivity is minus 110 dBm, let me keep this as minus 120 dBm, the noise, right? And it gave me a gain of 61 dB. But if we made this assumption, now we go back and see, is the sensitivity actually going to be minus 110 dBm, or is it going to be degraded because of this ADC noise? Is this low enough, or do we need to make it even lower? So that is what we're going to go through here. And let's see if I can explain through all this. So let's take the same example, bandwidth 200 kilohertz, and the noise figure of the RX chain only. Without the ADC, we said it was 2 dB. So what is the noise floor at the RX input? We know the thermal limit is minus 174 plus 10 times log of 200 kilohertz plus 2 dB is the noise figure. Okay, so we have only considered the noise from the RX chain but not the ADC. So what is that noise floor? The noise floor is minus 119 dBm. Right? Now if we consider the ADC itself, if you remember, we assumed it was minus 120 dBm. So you can see that's going to be a problem, but let's work through it. So without the ADC, the noise floor is minus 119 dBm. With the ADC, where we said the ADC noise is minus 59 dBm and we have 61 dB gain, this is minus 120 dBm. So we are getting two noises. This excludes the ADC, this is from the ADC, and they are uncorrelated. So what do you do when you have two noise sources? You have to actually add them. As not as an RMS, I made a mistake here, it's a mean square. Since these are uncorrelated noise, we have to square them and do a mean of it, and that will give us the total noise. So the noise because of RX chain itself, excluding the ADC, is minus 119 dBm. Noise because the ADC itself is minus 120 dBm. So how do we add it? This is how we add it, as mean square. So the first term would be, minus 119 dBm divided by 10. You do 10 to the power of this. Okay, so this is the noise power. Okay, so this is the noise power here, this term, for the RX chain only. This is the noise power for the ADC only. Add the two noise powers and do a 10 of log of this, and then the total noise power at the RX input now has become this. So you can see that this is actually higher than what we thought. So what is the effective noise figure then? So if this is the total noise power, I know that my receiver here has a 2 dB noise figure, but that does not include the noise from the ADC. If I now include the ADC and I extend this line all the way to represent a noise figure of this whole thing, what will be that number? That number will be the total noise power at the RX input, KTB plus noise figure bar. Noise figure bar is actually the one which includes also the noise from the ADC. So if you plug in all these values here, same formula and values, you will get 4.5 dB noise figure. So even though the receiver could have 2 dB noise figure, because this only has 61 dB gain and it has the noise as we said, coming at the input, if you include all of it, the 2 dB noise figure changes to 4.5 dB noise figure. And the sensitivity, you will not hit minus 110 dBm, you will actually get minus 107.5. That's what you're going to, there's a minus sign here, I think it got absorbed in there. It's not plus 107, it's minus 107.5 dBm sensitivity. Why? You will get minus 110 dBm if the noise figure was 2 dB, but that assumed that the ADC is noiseless. Given the ADC that we had assumed, it is actually going to cause significant amount of noise and cause significant degradation in the noise figure and the sensitivity accordingly. So what do you do here then? You want to increase the gain, yes, but you also have to improve the ADC to lower its noise, because again, increasing the gain has a problem of the jammers will saturate this receiver, and it will also, even though if let's say your receiver was great and you did not saturate and you could afford more gain, it could actually increase the swing here, the voltage swing at the ADC input, the peak to peak swing, which you don't want to exceed. So that is another problem that you can have for having too much gain. And we will actually do the exercise that I talked about earlier. It will actually capture that and show how different how we play around with it while trying to find the specs. So we have gone through gain, showed you some exercise of how we calculate the maximum gain, and then again, as the input changes, right, the input level changes, so over a wide dynamic range of the input, how we change the gain, that is again based on two things. Same thing as you said, ADC noise, how much will get reflected back at the input, and also the swing. Those are the two things that we will constantly monitor. And when we go through the exercise that I guess I've talked about it too many times, but have patience and you will get there, and you will see that how do we do that. The AGC, the automatic gain control over the wide dynamic range of the input. Next, let's talk about IP3. So IP3, as we have looked at earlier, it's a measure of the third order nonlinearity of the system, and in this case we are trying to find the IP3 right at the RX input. Why do we want to find the RX input? Because we are architecting it as a black box, and at the input we know the jammer levels which are going to be present for a particular standard. We will have different jammer scenarios, and for that we can calculate IP3, IP2 and all of that. So let's say we have a jammer scenario like this, right, where you could have a two-tone jammer that could be present at the input. It could actually be a multi-tone type of a jammer also possible, but we can take multi-tone jammers and model them as two-tone jammers. Okay, so if you have two-tone jammers with some P in value, each tone being P in, and the IM3 component is shown here, which will be generated, then the formula that we use is IM3 is 3 times P in minus 2 times IP3. So if you want to keep the IM3 at a certain level, the P in, you can derive what the IP3 would be for this black box. So let's take an example to go through this. Let's say the sensitivity, again, we use the same number, minus 110 dBm. And we have some two-tone jammers where each is 40 dBm each. Okay. So since the sensitivity is minus 110 dBm, which is kind of what is drawn here. So here are the two jammers which are minus 40 dBm each. Okay. Here is the sensitivity line which is minus 110 dBm, and we are saying this IM3 will be created. The question is, where do you want the IM3s? We are saying, okay, let's keep them 10 dB below sensitivity. Okay, we want these IM3s to be minus 120 dBm. So if you get that as minus 120 dBm, now you can actually calculate the IP3. What is the IP3 needed for this system. Okay, and that would be actually, if you put it in this formula, there's a straightforward way to do it. IP3 is the jammer power plus, what is this delta? Delta by 2. This delta here in this case is the jammer power is minus 40 dBm. IM3 we want minus 120 dBm, so the delta is 80 dB. So that delta by 2. So this is the Pn plus delta by 2. If you put these values, this is same as this equation here. It's a much simpler way rather than going round and round a little more. But if you simplify this, you will come to this step. The IP3 in this case will come to 0 dBm. So that's how you can say that IP3, if a jammer like this is present at sensitivity, we have this IP3. Okay, and that's how we quickly calculate it. Now, you will also do it for different power levels. For example, this was only at sensitivity. When you go to higher power levels, your jammer strengths could be different based on how the jammer profiles are defined in a particular standard. Normally when the signal is weak, the jammers are also weak. When the signal gets stronger, they allow even more jammers. Okay, so there is a jammer profile for that. So for there again, when you plug all this in, you will give you some IP3 number there too. Okay, so that's how we calculate IP3. And remember, this is at the very input we are calculating. So this is irrespective of the gain. The gain will change based on the dynamic range of the input, but that does not even factor into this calculation. The IP3 will also change based on the dynamic range here at the input, but this IP3 calculation is independent of gain, because we're treating this as a black box here. We're defining it at the input here. When you talk about IP3 of individual blocks, yes, they will depend on the gain that's before them. So that's important, and that's how you will derive the specs for individual blocks. But at a black box level, you don't need to worry about the gain. For the same scenario, we can do an IP2 also, which is also straightforward. You might have a jammer scenario where you have two tones, and the IP2, when it hits the mixer, the IM2 tone gets down converted to baseband near DC, which is where our signal is also down converted, and there it becomes a noise. So same way, let's say the jammers are the same, and I want my sensitivity is minus 110 dBm, and I want to keep it at minus 10 dB below, say minus 120 dBm. And in this case, the IP2 formula is the jammer power plus delta. Delta is 80 dB. The jammer power is 40 dBm each. Put it in, and it will give you a plus. This is a plus sign. It's not 140 dBm. It's a plus 40 dBm IP2. That would be the IP2 required for a jammer scenario like this, where you want to keep the IM2 contained to this level. Okay, so this is how we will find IP3 and IP2, treating it as a black box. Another case for IP3 is what we call triple beat, which is kind of one of those cases, very hard cases in cellular. So triple beat is basically, it's also a third order nonlinearity, where there are three tones, and if there are three tones, they could cause, if you go through a third order nonlinearity or third order expansion. For example, you have A1 sine omega 1t plus A2 sine omega 2t plus A3 sine omega 3t. You've got three tones, and if you do a cube of it, it will actually give you this scenario, which is what we call triple beat. So let's take a case here like this, where you have an RX signal, little signal. Okay, and here might be your TX signal. It's actually comprised of many subcarriers, but we can model it just as two tones, which I'm showing as TX1 and TX2. And there could be another unwanted, like a single tone jammer here. Could be an FM jammer, could be any other kind of jammer in the air, such that if you took the frequency, which is a frequency of TX2 minus frequency of TX1 minus the frequency of FJ, okay, with respect to this point, because this is our DC when you down convert it, that value, the subtraction of these three frequencies, will fall right here. Okay, so that is the case of the triple beat that we have. And let's take the same example here. Let's say the sensitivity is minus 110 dBm. And let's say the jammer power, this is minus 25 dBm, a very, very strong jammer. And CDMA used to have very strong jammer, now they have relaxed it. TX1, TX2, you can assume that, let's say, each of them is minus 28. Okay, and the IM3 that is caused, because as I said, we have three frequency components. If you did F1 minus F2 minus F3, the resultant value will fall right around this RX signal. Okay, So that one we want it to be contained again, and it's an IM3 component because it's coming with a third order nonlinearity. We want it to contain minus 120 dBm, 10 dB below sensitivity as an example. So now how will you calculate IP3? Remember, IM3 is 3 times Pn only if the jammer powers are the same. That is, if we had a two-tone jammer like this where both the powers are equal, then it works. But in this case where the three jammers powers are, so two of them are equal but the third one is unequal, or take the case where all three are unequal power levels, you could actually do an expansion of this as P1 plus P2 plus P3. So if all the power levels are equal, it will form 3Pn, but if the power levels are different, it's P1 plus P2 plus P3 for the three jammers. So put in the three jammer power levels here, and the IM3. Okay, so I'm calculating the IP3 as this. So what I did is I took this term and put it here. So I took this term over there. So IIP3 will be equal to 3 times Pn minus IM3 divided by 2. This is what I have. 3 times Pn is actually P1 plus P2 plus P3. So this term here is this minus IM3. This IM3 term is here, divided by 2 that comes from here will give me IP3. So putting all these numbers gives you a huge IP3 number, which is not realistic, but I've got some strong jammer power numbers here which are giving you an IP3 this way. But when you plug in for your particular case, if you have a triple beat case and you plug in the numbers, it will give you an IP3 number, and that's how you can calculate it. So that's how we calculate the IP3 for a black box and IP2 for this black box. Okay, the last thing that I want to cover here is RSB that we talked about, which is called residual sideband. So as I mentioned, you have the LNA, and after that it splits into two channels. These are supposed to be identical channels, and their phase is we provide a 0-degree clock, and the other one is 90-degree phase shifted. That's why it's I and Q. So 90-degree clocks would have a finite phase error. So it's not going to be 90, it could be 90.5 or 90.1 or more, whatever it is. So there is a phase error it will have. And the I and Q channels will always have some finite gain error. Why? Because even if you put this on, right, when you lay it out and all, there's always going to be some asymmetry somewhere, and you will get a finite gain error. Very small but finite gain error. So let's call that gain error as some GE. So phase error is phi E, gain error is GE. So because of this small gain and phase errors, we will have an RSB component that acts as an unwanted signal or like noise. What I mean is so imagine that you have a signal, right, which is comprised of multiple subcarriers. Okay, you don't have a single carrier carrying all the information, all the CDMA, WCDMA, LTE, Wi-Fi and all. They've got multiple subcarriers, and out of all the subcarriers, if I took a single subcarrier, right, just one of them, maybe there are say 1,000 subcarriers, and I'm just taking one of the subcarriers out of it. This will actually, when it goes through the asymmetry in gain and phase and reaches the digital and the digital processes it, it will actually see a RSB component which is shown here as noise. Why will it be noise? This is not a noise to this subcarrier, but it will be a noise to another subcarrier which is here. So whatever this delta is same as the delta here in frequency, and this will create an RSB component on the other side where the strength of that RSB component can be represented as roughly the phase error the whole square plus gain error square by 4. Phase error is in radians, gain error is an absolute value, and divided by 4. There is a lot of math, there is a lot of derivation, and if the phase error and gain error are small, then only this assumption is true. Okay, if the phase error and gain error were big, then this assumption is not true. Then we have to go back to those big mathematical equations and plug in the actual values to get the RSB component. But what this is giving you a value which is DBC, or relative value. Okay, you can see it is not dependent on what the strength of the signal is. So this is normalized to this signal, and that's why this value is kind of signal independent. Most of the cases it is signal independent. If you have a small signal, the noise created will also be small, but it will be relatively so many dBs below the main signal, which is given by this formula. If the signal became big, then also if you have the same phase error and the gain error, which is the case in most of the cases, then the relative strength of this will be same compared to the signal power. So RSB in a way is kind of signal independent, but there are different kinds of factors that come in when we switch gain, and when the signal gets stronger and the gain switching happens, so now all these numbers actually change. So but in general you can treat it as more like whatever is the gain error at that point between I and Q channels, whatever is the phase error, based on that we get an RSB component, and that little component acts as a noise to another subcarrier which will be here. So if I drew all the subcarriers, they will all have their components all over, and they would be a certain level relative to the main signal, and we represent them more like dBc. So for example, if you said RSB is minus 36 dBc, what that means is if you took one subcarrier or all the subcarriers and their power and all the power of all the RSB components, that is 36 dB below. Okay, so that is what residual sideband means, and this is another kind of noise that we are introducing. So we don't want this to be a big number. We want it to be as small as possible, because we already have too many different kinds of noises. Adding this is another noise only will cause us more problems, and we will have more of this in the exercise that we are going to do next. So there it will become more clear of how RSB limits the SNR of the modem. How do we use all these things that we talked about, right? Gain, noise figure, IP3, IP2. How do we come up with initial values for these things, treating this as a black box when there is a huge dynamic range in the input? How is the gain going to change with the input? How will the noise figure need to change with the input? How the IP3 needs to be architected with the inputs? All that we're going to do in the next exercise after this, so that all these things that we talked about will become more clear then.